Okay, so in the last class we were discussing about the design of singly reinforced beam. Okay, and okay, so you do one thing. All of you open your IS 456, and now I will share the PDF with you. And because okay, so now I am going to share the PDF with in your group. All of you take it. Okay. Okay, so this is the PDF I am going to share with you. Okay, so I have shared the PDF in the group. Okay, so all of you please take it from Nanu Padum. Nanu Padum, please share the PDF in your student group. Okay, so okay, so in the last class we have discussed this example 6.1, and I think in example 6.2 also we have been 6.2 and 6.3 has been discussed in the last class. Is it? Yes or no? I think up to example 6.3, 6.4. Yeah, up to example 6.4, I think it has been discussed in the last class. Is it? One chin? Yes, sir. Okay, thank you. Okay, so let us see from this example. Example means this is example 6.5. Okay, so I hope all of you have got the PDF. I hope all of you have got the PDF and you can see the screen also. Okay, so you can see the screen also. Okay, so now if you can read the question, in this question you have to design the beam with all the you can see here design the beam with all the necessary checks. That means first we have to design the beam. That means we have to find the width of the beam, we have to find the depth of the beam, then we have to find out the area of steel, and then since it is written here with all the necessary checks, what we have to do after designing it, we have to check our beam for deflection as well as we have to check it for shear reinforcement. Okay, after designing the beam we have to check whether we have provided the shear reinforcement properly or not. We have to check it. Then we have to check whether our beam is safe for deflection or not. These things we have to check. Okay, so this is going to be a little bit lengthy problem. So please try to understand. Okay, whenever I explain, you try to understand, and if you have any doubt after explaining, then you can ask me. Okay, so let us start the problem. So in this question, a simply supported beam is given to you and it is supported on two masonry walls, and the thickness of walls are also given 230 millimeter, and center to center distance is also given 6 meter, and it is given that the beam is carrying an imposed load of 15 kilonewton per meter. That means it is your live load. Okay, imposed load is nothing but your live load. So imposed load is nothing but the live load is given 15 kilonewton per meter, and you are asked to design the beam with all the necessary checks. Okay, and you have to use M25 grade of concrete and Fe415 grade of steel. Okay, so first write down the given data. LCC means L for length, CC means center to center. Okay, so center to center length is given 6 meter. Imposed load is given 15 kilonewton per meter. FCK, FY, these values are given. Okay, so now if since you have the PDF with you, you can see here assuming a trial depth of 500 millimeter, and how they have assumed it, L by 12. Okay, L by 12 means okay, L by 12. So L by 12 means you can see this PDF. Okay, just go through the notes. Before the numericals, we have the notes. You can see here. You can see here determining the dimensions of the beam and area of tensile reinforcement. Can you see the PDF? Can you see this page in the PDF? Can you see this part in the PDF? Yes, sir. Okay. So here you can see here. You can see here assume suitable value of depth and width. Okay. First we have to assume it because the values of width and depth are not given. Okay. And if we don't assume these values, we cannot proceed to the next step. Okay. So to start with, the depth of the beam can be assumed as L by 12 to L by 15. Okay, and this L, always remember this L is your center to center distance, not the clear span. Okay, always remember this L is always your center to center distance. Center to center distance. So it is to start with, the depth of the beam will be assumed as L by 12 to L by 15, and width may be assumed as 1 by 2 to 1 by 3 of depth. Okay, so in this question, we have assumed the depth equal to L by 12, and then we will proceed to the next part. Okay, so let's go to the problem again. Okay, so L by 12 equal to, you have got 500 millimeter. Okay, and B equal to, they have assumed half of the depth. Width of the beam is half of the depth, so it is 250 millimeter. Okay, so next effective depth will be equal to 500 minus 50. Here they have assumed that the effective cover is 50 millimeter. Okay, here they have assumed that the effective cover as 50 millimeter. Okay, so if you assume 50 millimeter, then the effective depth will be total depth minus effective cover, so it will be your effective depth. Okay, so 450 millimeter is the effective depth. Okay, so next what we have to do, in the last class I told you that first, before going to any step, we have to find out the effective span. Okay, so can you tell me the clause number for effective span? Can anyone tell me the clause number for effective span? One chain, can you tell me the clause number? Anyone, if you know, you just tell me the clause number. Nanu Padung, can you tell me? Likhania? Don't know. Okay, anyone? Can anyone tell me the clause number to find out the effective span? Clause number from IS 456. Okay, it is the clause number 22.2. Okay, clause number 22.2. I told you in the last class. Okay, so all of you, again I am telling you, all of you be prepared that your you may have to appear your exam offline. Okay, you may have to appear your exam offline. So in that case, if you don't remember the clause numbers and if you don't know the procedures, then it will be very difficult. Okay, then it will be very difficult for you. So always I am telling you, whenever we are trying to solve some numericals, and if we are using IS 456, you try to remember the clause numbers. This is the clause number 22.2. Okay, clause number 22.2. According to this clause, we have to find out the effective span. Okay, so for finding out the effective span, we have to find out two values. First one is, you can see here, flare span, first value will be this one. Flare span plus the effective depth of slab. Okay, first value will be this one. Flare span plus effective depth. And the second value will be center to center distance. Second value will be this much. Second center to center distance of supports, whichever is less. So for finding out effective span, we have to find out two values. First one is flare span plus effective depth, and the second value will be center to center distance of supports. Okay, so whichever value will be less, that will become the effective span for the respective beam. Okay, beam or slab. So you can see here, center to center distance is given directly. It is given in this case. It is 6 meter. So the second problem is we have to find out clear span plus effective depth. So clear span will be 5.77. I hope you know what is how to find out clear span. It is the center to center distance minus width of one wall. Okay, that will be your clear span. So clear span is 5.77 and effective depth you have got 450. So that means here it is 0.45. So if you add these two values, you will get 6.22 meter. Okay, so now you compare the two values. 6 meter is the smaller one, so it will become your effective span of the beam. Okay, it is very easy. No need to there is no what to say logic behind this. Only you have to find out these two values, compare the two values. The smaller value will become your effective span. Okay, as per IS 456. So in this case, we have got the effective span as 6 meter. So next, see how to find out the design load and factored moment. Okay, so first you have to find out the self weight of the beam. Okay, all of you know what is self weight. Okay, so how to find out the self weight? It is your, this 0.5 is the depth of the beam, 0.25 it is the width of the beam, and 25 it is the unit weight of RCC. You can see here it is written here, taking unit weight of RCC as 25 kilonewton per meter cube. Okay, so this value is always constant. Unit weight of RCC is always constant. Okay, this value is always constant. Unit weight of RCC is always 25 kilonewton per meter cube. Okay, so depth into width into unit weight. So if you multiply these three values, you will get the total self weight of the beam. Okay. Okay, so now you have got the self weight of the beam as 3.125. Okay, and in our question it is given that the imposed load, that means our live load, is 15 kilonewton per meter. Okay, so therefore the total load will be 15 plus 3.125. You can see here the total load will be this much. Okay, so for finding out the design load, you have to multiply the value by load factor 1.5. So multiply the value, so you will get 18.125 into 1.5. That means our design load will become 27.2. Now the design moment will be, all of you know the formula for simply supported beam. It will be WL square by 8. Okay, WL square by 8. So you can use the formula and you can find out the value. W value you have got already, 27.2. L is center to center distance, which is 6 meter, or it is the effective span. Okay, WL square by 8. This L is your effective span. This is the design load and this is the effective span divided by 8. So effective span was 6 divided by 8. So our design moment will be 122.3 kilonewton meter. Okay. So next, after finding out the design moment, what we have to do, just like the previous problem, what we have to do, we have to find out the moment of resistance. Okay, from the moment of resistance equation, we will find out the area of steel. Okay, so now we will check whether our assumed depth is correct or wrong. Just like the previous problem, this value, all of you know it. This value you will get from IS 456, and it will be, yeah, clause number I think 38. In clause number 38, for Fe 415 steel, Xu max by D value is 0.48. Okay, so now the value of Ru you have to find out. Ru means 0.36 FCK. This value you have to find out first. Okay, so in this case, after putting all the values, we have got Ru equal to 3.45. Okay, so next, after getting the value of Ru, after getting the value of this factor Ru, we have to find out the effective depth required from this equation. Effective depth required will be square root of mu divided by Ru into B. This equation I have shown you in the last class, or you can see the notes. Okay, you can see the notes because you have the PDF. D required will be calculated by this formula. Okay, mu, that is our design moment, Ru, which is already calculated here, and B is the width of the beam. Okay, so from this equation, after putting all the values, we have got the D required, that means effective depth required is 376. But in this problem, we have after assuming, we have got the effective depth is 450. That means our assumption is correct or wrong. The required value we have got 376. The required value of effective depth we have got is 376. And we have assumed the value of effective depth as 450. So can you tell me whether our assumption is correct or wrong? Manjin, our assumption was correct or wrong? Hello, can you hear me? Hello. Okay, assumption was correct or wrong? Vanchin? Okay, okay. Okay, so I will tell you that our assumption was correct. Okay. Okay, assumption was correct because our required value was 376, but we have assumed 450, which is more than the required value. Okay, that means our assumption was correct. Okay, so in some cases or in some problem, after solving the numerical, you can see that our required value is more than the assumed value. So in that case, what we have to do, we have to change the assumption. We have to change the first step, then again we have to proceed to this step. Okay. Okay, so now here you can see here, since the depth of the section is more than required for balance section. Okay, this D required, whatever we have got, this is the required value of effective depth for our balance section. Okay, this is the required depth for a balance section. Okay, wait for 1 minute. Okay, wait for 1 minute. Okay. Okay, so this D required, it is 376. That means this is the required depth for a balance section. Okay, this is the required depth for a balance section. But in this case, we are assuming, or we are providing the effective depth equal to 450. That means you can see here, since the depth of the section is more than required for balance section, the section can be designed as under reinforced section. Okay, the section can be designed as under reinforced section. So adopt D equal to 500 mm and B equal to 250 mm. Okay, so now this is the exact value of our effective depth. Okay, this is the actual value of our effective depth. It is not exactly 450 actually. The exact value will be this one. This is the more accurate value. Okay, so you see this value, and if you have any doubt, you ask me now. See how they have calculated DE, or this is the actual procedure to find out the effective depth. Do you understand how they have calculated this one? All of you? No, sir. Okay. Okay, wait. I will I will show you this one. Okay. Wait, okay. I will show you how they have done this one, because without the cross section of a beam, I cannot explain this one. You will not understand this one. Okay. So now see this beam. Okay. Now see this beam. Okay. So now this is the beam. Okay. So the total depth is from this portion to this portion. Is how should I edit? Okay. Wait. Okay. Okay. So this is our beam. Okay. From here to here. From from this level to this level. This is our, what is this? This is our total depth, capital D. Okay, this is our total depth. Our total depth is this much. This is our capital D. From from this level to this level, this is our total depth. This is our capital D. Okay, total depth of the beam. Now our effective depth will be, I will tell you, effective depth will be from this to this line. Can you see? Our effective depth will be from the topmost layer of the beam to the center of this reinforcement. Okay? Can you see this, all of you? Can you see this, all of you? This is our D. Okay. This is our small d, effective depth. Okay. So now this portion, this small d portion, this portion is our effective, this length from this portion is, can you tell me what is this? This length is called what? This length is called, this is our clear cover. Okay, so clear cover. From the surface of the reinforcement to the surface of the concrete, this length is our clear cover. Okay, so now in this case, our clear cover is how much? So our clear cover is 20. Okay, so 20. Our clear cover is 20. And our total depth was 500. It is our 500. Okay, so D was 500, clear cover is 20. Okay, so now we need the distance up to the center of the reinforcement. Okay, so now what is this? Can you tell me what is this? What is this? Can you tell me what is this? Anyone?
Stirrup.
Yes, good. It is the stirrups. Okay, so now in this case, the stirrup diameter is how much? You can see in the PDF. The stirrup diameter is, this is our stirrup. Okay, this is our stirrup. And the diameter is how much? This is our stirrups.
8 mm.
Yeah, 8 mm. So you can see, to find the value of D, small d, that is our effective depth, we have to deduct total depth. From the total depth, we have to first deduct the clear cover. So if you deduct clear cover, you will reach the surface of these stirrups. Then we have to deduct the diameter of the stirrup, is it? You can see here, you have to deduct the diameter of the stirrups. So which is our 8 mm. Then after deducting the diameter, still you have this space left. And this will be how much? This length. Can you tell me this length will be how much? This length will be how much? This portion. From the dotted line to the solid line, this length will be how much? Raju, Wanchin.
10.
Yeah, if you use 20 mm diameter bar, this is just the half diameter. This is just the radius, half diameter of the bar. Okay. So now can you understand now? To find out the effective depth, we have to deduct total depth minus clear cover minus this diameter of stirrup minus half of the diameter of main bar. Okay. Do you understand now? All of you, do you understand now?
Yes, sir.
Okay, so now this is the thing they have done. See here. This is the total depth minus clear cover minus area of the stirrups or the diameter of the stirrups minus half of the diameter of main bar. Okay, so they have got 462 millimeter. I hope all of you have understood this problem, this part at least. Okay, so let us see next how to find out the area of steel. This is a very simple procedure. We have solved it so many times. Okay, just see the calculation. Just see the calculation. I hope all of you will understand this one. I'm not going to explain this part because this is a very simple one. I'm not going to explain this one. But if you have any doubt or any confusion, you can ask me. See the area of steel. Okay, so this class will end, I think within 2 or 3 minutes it will end. So after the class, just after the, if the class will be stopped here, you join after 5 minutes, okay? When the class will be over, this first class, I will give you a break of 5 minutes, then we will join again. Okay, just see the area of steel required. It is very simple calculation. Okay, so I hope all of you will understand this part, at least up to the minimum area of steel. And then this part, area of steel and minimum area of steel. Number of bars also, I hope all of you have understood this one. Is it?